So again, when this thing decides to not write. Okay, try again. So basically with Bayes' theorem, it lets you kind of turn around conditional probabilities. So probability of A given B is probability of B given A. If we wrote this down last time, but do it one more time, I guess. That's probability of A. And then same thing on the bottom. All right. And we said what this is useful for is, I mean, usually in real life, we know the conditional probabilities one direction or the other, but we want them the other way around. So for example, this is like, what this is used for, let's say Ty is gonna, I don't know, say he gets 30% of his stuff from a company and he gets a bad batch 5% of the time. And he gets 80% of his stuff from another, not 80, that's too much. How about 60 from another company, and they don't have bad batches as much. And he gets the rest of it from a third company, and they have them pretty often. And I say, well, why does he want to do that? Well, maybe company C is a whole lot cheaper than the other ones are. So, I mean, this is very plausible in the real world. But then the question comes up, hey, if he gets, let's assume he gets a bad shipment and he's kind of planning from the worst. And he wants to know what's the probability that he got it came from, say, company B or something like that. So, because most worst case scenario type things are going to be using Bayes' theorem in the real world. And I mean, the real world worst case scenarios are a big part of like planning your business. So that's kind of why it's useful. So let's go ahead and do a couple more just so you get a feel for how it works. Even though, again, this will be like one question on the first test, one question on the final. So, I mean, it's not going to be huge in this class, but I think it's important that you have a decent understanding of it. So it says there's a 20% rate of a certain virus for the at-risk population, and preliminary screening is correct 90% of the time. So if someone is randomly selected from the at-risk population, what's the probability if they have the virus if it's known that they have tested positive in the initial screening? So okay, so it says, so we know the probability of having the virus if you're, work. There we go. So probability you have the virus if you're at risk is 20%. So we're going to say V is having the virus, R is being at risk, and let's say P is you tested positive for the virus. All right. We know that the preliminary screening is correct 90% of the time. So the probability that you have the virus, given that you test positive, is 0.9. All right. It says if someone is selected from the at-risk population, what's the probability that they have the virus if it's known they have tested positive in the initial screening? So, wait, did I read that right? Oh, crap. This one's backwards. So, okay, if you have the virus, 90% of the time the thing will. I hate reading. Reading is the hardest part of this class, I think. Oh, no. It says under a preliminary screen test is correct 90% of the time. Okay. Actually, I think that's just saying. It's just saying the probability. So the probability that it says yes if you have the virus is, and then also the probability. Okay. Keep going. So what's the probability they have the virus if they did test positive? So, is this even Bayes' theorem at all? It doesn't really feel like it is. Because, okay, we want to know what's the probability that you have the virus given that you tested positive. So Bayes' theorem would say that's the probability that you test positive. Or sorry, the probability you have the virus times the probability you test positive given that you have the virus. Probability that you have the virus, probability that you test positive given that you have the virus, probability you don't have the virus, probability you test positive if you don't have the virus. Right. This is really boring, isn't it? I don't know. I feel like y'all are being really, really quiet. I think Christopher needs to break the news. I just had to pick somebody. Okay. So the probability this person has the virus is 0.2, right? At least among these because they told us we're just looking at at-risk people, so that given at risk doesn't do anything. Okay, the probability tested positive if they have the virus is 0.9. Right? Same thing on bottom. Probability have the virus 0.2. Probability that they have the virus if they test probability they test positive if they have the virus 0.9. Okay, probability they don't have the virus. What's the probability someone in this at-risk group doesn't have the virus? 0.8. How'd you get 0.8? Yeah, it's everything. I mean, 20% have it, so 80% don't. Okay, what's the probability that you test positive even though you don't have the virus? So what it actually said in the problem is this test is correct 90% of the time. So if it's correct 90% of the time, what's the probability you're going to test positive but not have the virus? 10%. Right? So just punch all that in. So that's 0.18 divided by 0.18 plus 0.08 is 0.26. And again, my pen quit working. I don't know what's up with this thing. 0.26. So 18 over 26 is, according to my calculator, 69. So 69.23. Yeah. So it's kind of counterintuitive Because, I mean, on one hand, I told you, hey, this test is right 90% of the time. So you go down and you get tested, and it says you have this virus. What's the odds that you actually have the virus? It's only 69%. Does that seem weird to you? This goes back to what we said the first day. Hey, statistics don't lie. Statisticians do lie. So I mean, they tell you, hey, this test is right 90% of the time. That doesn't mean that you can be 90% sure of what the test tells you. So it's, yeah. All right, so this was 3 decimals, so 0.69. All right. I want to find one where there's 3 groups. Because if you can do 3, you can do any of them. I mean, they're all kind of the same once you get past 2. But 3 coins, 6. This is not what I wanted either, but it's just such a fun problem. What do y'all think? Study researcher sites and the problem of 3 coins. So one of which is biased, so it turns up 65% of the time. You select one of the coins, toss it 4 times, and obtain 4 heads. What's the probability that this is the biased coin? So do you think it's weird to get 4 heads in a row? Yeah. What if, I mean, 65 is about 2/3. If it's supposed to get a heads 2/3, do you still think it's weird it gets 4 heads in a row? Yeah, you would think out of 4 tosses, you should get 1 tails at least in there, right? So, but how would you actually find the probability that this is the best? I have fallen down in the middle of class. So, when it happens, because it will happen at some point, maybe not in this class, but if it does happen in this class, feel free to laugh. It won't hurt my feelings. So, let's actually